Now, let's talk about the forces due to magnets. Okay, obviously we've seen that you can take two magnets and stick them together. Let's take another look at our nice magnetic field pattern around this dipole. If I have these two magnets here, they like to align, I think these are mislabeled, such that they like to stick together with north to south, south to north, okay? So that's why you see it goes like this. They tend to align, each one aligns in the direction of the field of the other, and then they tend to stick together like that. But what this doesn't tell us is how how do these forces arise between two magnets? And you'll play with magnets in DL. Suppose we have a charged particle moving in a magnetic field. Now in this picture, this charged particle Q is traveling in this direction, which you can think of as sort of into the screen. It's sort of a three-dimensional perspective view of it. Now, a magnetic field will exert a force on this charged particle, which is equal to Q times the velocity of the particle times B. I don't think we ever quite encountered a force like this in Physics 7a or B at all, right? Because it depends on the velocity of the thing moving in this field. That's a very weird thing about magnetic fields. And there are a lot of strange effects that you can get with magnets, and when you have strange effects, of course, charlatans start to use them to make false medical cures and so forth. So I imagine there are people wearing magnetic bracelets for some pain, thinking that that's going to do something, but it's not, I can assure you. Nor will the magnets that you put in the soles of your shoes help you, help your life energy increase or something. So here we have this charge moving in this direction. A magnetic field is pointed down, and it's perpendicular. Even though I didn't draw it like that, try to imagine that that's perpendicular to the velocity. And now we want to know the force. We know the magnitude of it is Q times the velocity of the charge times the magnetic field. And this, by the way, gives us the units of the magnetic field, because we have Q times V times B. Well, B is in units of F over Q times V. So it's force, newtons, over charge, coulombs, times V, meters per second. So you get newtons second per coulomb meters. So there are two right-hand rules we need to learn. And the first one is this. If you take your hand and you stick your thumb in the direction of motion of the charge, which is into the screen now, and put your fingers in the direction of the magnetic field, then your palm will push the charge in the direction of the force. So that's kind of easy. You can imagine pushing with your palm, right? So whichever direction the charge is going, your fingers go in the other direction. Make them 90 degrees apart. We're going to mostly deal with the case where the magnetic field is 90 degrees from the direction of motion of the charge, so it's easy to visualize. And then the force is perpendicular to both the magnetic field and to the velocity. In terms of vectors, if you've done vector calculus or vector algebra, then you know that this is the vector cross product, V cross B. So that's the right-hand rule. Your thumb goes in the direction of motion of the charge, your fingers in the direction of the magnetic field lines, and then in that case your palm pushes the charge. So let's actually try that with a real beam of charged particles. Here we go. We can make our beam of charged particles by putting a nice high voltage across this in this direction, so that this is negative and this is positive, and these are electrons moving to the right through a slit. So there's a sort of flat beam of electrons, and as it moves, it encounters that phosphor screen, and you can see the nice green glow of the electrons hitting it. Now, electrons are negatively charged, right? So immediately we hit with our right-hand rule that we have one additional thing to encounter. So what we're going to do is put a magnetic field on these particles. And let's see, I have this one where it's labeled nicely, which this one is south. So this is the north field, the north pole of this magnet. So field lines are coming out and going back around into the south pole. So out here in front of the magnet, the field is basically pointed like that. So I'm pointing the field away from me. All right, so right-hand rule, field lines in the direction of your fingers, thumb in the direction of motion. My palm pushes down, but they're negative charges, right? And our formula carries that Q. So it will deflect it up, right? So if I put this near, it should deflect the beam in the upward direction. Did I get it right? Yay, physics works again. Now what happens if I turn it around? Now I have a field pointing this way. It's exactly the opposite, and it deflects in the other direction. So that shows you that the force is due to the magnet. I didn't touch anything, right? Whoa. One strong magnet. So let's play with the units of magnetic field for a minute. Now we've seen that thing I asked you to remember last week. 1 Newton per Coulomb is the same as 1 volt per meter. Our magnetic field unit, the Tesla, is 1 Newton second per Coulomb meter, named after the famous physicist and crazy man Nikola Tesla. So what is another expression for the Tesla unit? Go ahead, do the calculation, check it with your neighbor. There's a simple way to go from newtons per Coulomb to Newton seconds per Coulomb meter.